Um, the topic of the presentation today is the durability assessment of alkali-activated calcined clay with GGBFS and chloride and carbonation environment. So my name is Samuel de Carvalho Gomes. So my supervisor is Professor Arnold Carson. Co-supervisors Dr. Wangley and Dr. Kirk. So I'm a PhD candidate at the University of Technology, Sydney, UTS. One quick introduction about the huge demand of for new low carbon concrete and some new composites with a low environmental impact. So geopolymer concrete or also alkali-activated concrete are considered sustainable materials, typically produced from byproducts such as fly ash, GGBFS, or other materials with high concentration of aluminum silicate, which can be activated directly with one alkaline solution. As you guys can see, this is a famous building on here in Queensland, in Brisbane, at University of Queensland, the Global Change Institute. So this building is around 40% of the buildings made by geopolymer concrete. So one overall picture about the raw materials to produce alkali-activated concrete in Australia. So fly ash, as you know, has been broadly used in Australia for decades. So 1.6 million tons each year it's used as a partially replace OPC in Australia. However, as we've been shifting to this green energy recently, so you were expecting some drastic reduction of fly ash availability in some future in Australia. Same case of GGBFS, as you call it, slag. In Australia, you use around 1.5 million to the same reason of fly ash to replace OPC and some small applications, but around 0.5 million tons are produced in Australia, but 1 million tons GBFS it's imported from overseas. So because of this, you're looking for new raw materials to produce alkali-activated concrete and also low carbon concrete to replace OPC. So recently, calcined clay being a really strong and potential candidate as a precursor for this type of material. So a huge amount of clays for alkali-activated materials are available in Australia and around the world. So calcined clay can be defined as a product with a large specific surface, especially from the calcination and grind of some clay-rich materials in silica and aluminium. So and then the high purity calcined clay you call metakaolin. So commercially, you know this material as metakaolin, but normally it's very important to define these metakaolin. When I'm talking about metakaolin and calcined clay here, I'm talking about the content of kaolinite on the material. So when the material has a low concentration of kaolinite, and you call this calcined clay, sometimes low-grade calcined clay or low-grade metakaolin. So when I'm talking about metakaolin, it's a 95-100% purity of material. So here's also an overall picture of Australia. So sorry, as you guys can see on the picture on the bottom of the picture on the bottom, Australia has a huge some reserves of different types of clay. So as the previous study already showed that clays can be divided by its internal composition, like one as you know, kaolinite is a famous one, and to one type, a lithium. So you have some large amount of clays around Australia that can be used as resource for duopolymer and also LPC and LC3 concrete. So some studies on LC3 concrete have revealed that the carbon footprint for 2,1 and also 1,1 clay is around between 132 CO2 kilograms per kilo and 270 CO2 grams per kilo, which is much less than the emissions produced by the normal OPC clinker, which is around 100 CO2 grams per kilo. So the research gap of this specific research inside of my thesis was assess the carbonation resistance of this composite of calcined clay with GGBFS. And the research gap around that is like there are existing studies with focus on geopolymer based on fly ash, especially fly ash and metakaolin. However, the carbonation resistance of calcined clay geopolymer or GGBFS blended is still a topic to explore. So the influence of alkaline models and also the alkaline concentration in amorphous and calcium content on the carbonation resistance of the calcined clay is still a topic to be explored. So also the chloride diffusion of this composite, the research gaps around about, as you know, a lot of studies have been applied some chloride transport test methods from normally OPC in a natural diffusion method and also an accelerated diffusion method. So you on this specific project, you using these results to confirm, and then for a big database that from our research group to confirm if these methods that was developed to OPC can be replicate on alkali-activated materials. So also you don't have enough data on the chloride resistance of calcined clay geopolymer blended with GGBFS. So the first part of this chapter was focused on the carbonation on my PhD, focused on the carbonation resistance of the composite of calcined clay GGBFS. The main objective of this specific chapter, I don't have time to explain everything today, but feel free to hit me up later. But and this specific chapter which was focused on a carbonation. The objective was to clarify how the alkali solution concentration and the calcium content on the raw materials and the joint impact on the shrinkage process and the long-term carbonation resistance in a natural way. So on this study, you compromise the examination of also the mechanical properties, the pore size distribution, and 1 year observation of natural carbonation trends. So further, you used some electrical chemistry tests to assess the potential corrosion risk of the steel bar induced by the accelerated carbonation. So for the materials and methods for the carbonation experiments, that's my chapter 4. I'm showing you like only for mixed designs, but you have more on my thesis. But these specific ones are the ones that had more compressive strength and perform better. So here you can see this 70 cc means like 70% of calcined clay, and 30S means 30% of slag, and 8 is the concentration, activated concentration, 8%. So we also did the same mix with 70% of calcined clay, 30% of slag. However, you increase the activate concentration to 10. Same thing, you use 50% of calcined clay and 50% of GGBFS with 8 and 10% 50% of activate concentration. So the calcined clay used in this study was you call low-grade calcined clay, as you only have 50% of amorphous phase. It's a commercial calcined clay. You import them from France. So when you blend it with GGBFS, sodium hydroxide, sodium silicate, that's the mixed design, and here's the sample, one of the samples of the blend, with also the sample for the shrinkage test. So here the compressive strength for the carbonation test. So as you can see here, at 28 days, we have like some samples with all the mix perform something between 30 MPa and 54 MPa. So as you can see, the high proportion of percentage of alkali concentration with 10 had like the highest compressive strength, something above 50 MPa. All the samples with concentration, alkaline concentration, and 10% had like over 50 MPa. Either for the 70% of calcined clay and 50% of calcined clay, both performed very well and then had a compressive strain over 50 MPa. However, the two mixes, when like had like only 8% of alkaline concentration, they had something around 30 MPa. So when you expose these samples, these 4 samples to the accelerated carbonation and also to the natural carbonation over 1 year, that's the average of carbonation depth for the accelerated and natural one. Also, in terms of to compare with the performance with the normal OPC, you did like to reference OPC blended with 40% of slag, with 40 MPa and 50 MPa, just for comparison. So as you guys can see, all the geopolymer concrete with these 4 fast mixes that I showed you before, guys, before that had something between 30 and 55 MPa compressive strength. From the week 1 to week 8, you have a really high carbonation depth when it comes to accelerate carbonation. So the samples was exposed to 2% of carbon dioxide on the carbonation chamber. So after 8 weeks, as you guys can see, the sample with 70% of calcined clay, 30% of slag, and 8% of alkaline concentration was completely carbonate, as you guys can see on the bottom here. That's the sample. So all the samples with exposed to 8 weeks of 2% of carbon dioxide had a really high carbonation depth, around 20 and 70 millimeters. But as you can see, the OPC with 40 MPa and 50 MPa had something around 10 millimeters, and the OPC blended with 40% of replacement of slag and had like 50 MPa has something about 7 millimeters. So this is for the accelerated carbonation. But when it comes to the natural carbonation, after 12 months, we still have a really high carbonation depth. As you can see, guys can see, 17, around 18 millimeters after 1 year. This sample had a really high carbonation depth, which you also guys can see here. Natural carbonation was very high. However, the OPC blended with slag, you guys can see both of the samples after 1 year exposed for the same condition, they have only around 4 millimeters. So the main questions when you so this high carbonation was as you already knew, like previous research already showed that like the geopolymer and alkali-activated materials has this really high carbonation depth. But recently, some study already showed that this carbonation depth was was a topic of so many studies that was showing that this carbonation most of the time was not this carbonation um, was doing the pore solution of the indifferent microstructure of the geopolymer concrete. So on this case, most of the study was showing that the phenolphthalein, this is particular phenolphthalein test, always overestimate the carbonation. So because of that, you move to the actually to see if this area that was showing as was carbonated was truly could pose a risk to the reinforcement bar. So you perform some pH measurements on the case of the same mix design. I will just show you guys. There was especially the ones that was completely carbonated. So, and you move to the pH. So you did for the uncarbonate 28 days. All the materials are sealed. So the four mix design I showed you guys before, they all showed a really high pH for the first 28 for after 28 days. They showed around something above 12.5 pH, which is very close to the OPC concrete pH, very alkaline. So you use two different methods for this 28 days. You use the pore solution extraction. You also use the pounder pH measurement. So after that, you expose all the samples for the same conditions for the accelerated carbonation 8 weeks. So as you can see, this is this purple bars, and then they all show a very similar trend. Something like after 8 weeks, we extract the carbonate part that was shown that was carbonate, and it was something about 10.8, 10.6 for all the mixes. Same thing for the natural carbonation after 6 months and 12 months. They kind of have a very similar value, which was something above 10.5. As really interesting thing that you noted before that the phenolphthalein experiment that we showed before, they pretty much calibrate for the all normal OPC. So when it shows that, as you guys see here, the OPC, this white area, it's carbonated. This area is truly carbonated. This area, the pH of this area is something around 9. So this particular pH measurement shows exactly the trend that not only our study was showing before, but like some recent studies show in the past years that this actually this pH, it was showing that this only the partial part of the composite was carbonate, which was only the pore solution. So which was in most of the studies show that this is particular pH doesn't pose any risk to the steel bar. So to confirm that, you did like some electrochemical tests based on electrical resistivity and steel corrosion potential in concrete based on the ASTM 876. So this is on your right is the sample that you use to perform this test. And this was, as you guys can see, there is a reinforcement bar inside of the alkali-activated specimen, and you use the similar specimen as you use Dr. Babayi Khan and my supervisor Arnold used in 2008 in their paper. So you perform that, and the results of the electrochemical measurement shows, as you guys can see, like the steel bar, like the steel bar, it's in directly contact with the carbonated. You use the accelerated carbonate for this specific one. So as you can see, they are in contact with the steel bar. And as you guys can see on the picture C on the bottom, the corrosion potential shows that there is a really low risk to the carbonation or to the corrosion of the steel bar, even after 56 days exposed to the accelerated carbonation. So as I showed you before, this pH is still something, this area that shows carbonated. You measure the pH before, it is still like something a bit around 10.8 or something like that for both of the experiments. So on the A is you have this area, you have this is a specimen with 70% of calcined clay, and this is 50% of calcined clay, 50% of GGBFS. So also the polarization resistance, showing that also there's a really low and moderate corrosion rate probability on the both of the samples. So based on that, you draw some conclusions on the carbonation, based on the carbonation. So as I said before, the increasing of concentration of 8 to 10% of alkaline concentration really improve the mechanical performance. So you have after 28 days something around 54 MPa for the composite with 50% of calcined clay, 50% of GGBFS. And also the carbonation resistance shows that on the accelerated conditions, even on the acceleration condition, natural condition, the pH is still maintain like a really high pH, which is prevent the steel corrosion. And you prove that also on the stable half cell potential and polarization resistant test, which confirm that there is a really low risk of potential corrosion. So, and then the main conclusion about that is that although accelerated carbonation is widely used for OPC concrete, carbonation depth from the accelerated carbonation can significantly overestimate the carbonation in calcined clay, GGBFS, alkali-activated concrete, and then normally all the geopolymer concrete. So electrochemistry tests such as corrosion potential and polarization resistance are required to accurately evaluate this corrosion process in geopolymer concrete, and in our case, the calcined clay GGBFS alkali-activated materials.